let's say that, and let's forget about these new nodes. Let's say that I run DFS in this particular graph. Would my DFS algorithm work, or would it end up in a loop, infinite loop, or would it just, yeah, those are the only two possibilities. Would it still work and search all the nodes and explore all the nodes, or would it end up in an infinite loop? I'll just type it out as options. Let's say A is in loop and B is, type in A or B. I need answers from all of you.
And if you just typed something out, we can't see it. So I don't know if you meant for that to go on the screen somewhere.
Oh, okay.
Thanks.
Okay, okay. Sean and Eric, it won't be A that is an infinite loop, because think about it. What is the algorithm for DFS? If we have already visited a particular node, we won't be visiting that node anymore, right? If visited is already true, then we are not exploring. If visited is false, only then are we exploring, right? So in this particular scenario, let's say I start off with B, right? I go to F, then I go to A, and when I check for B again, that is the next edge from A, I see that B is already visited. So because B is visited, I'm not going to explore B again. I'm going to jump to some other node and come back right back to B again, and then search for D or C or things like that. Yes, it always checks before visiting the node. Does that make sense, Sean? Perfect. Thank you. Let's see. Okay, so one thing that we can do to figure out if we have acyclic graphs is apply some algorithm called a topological sort. A topological sort is in essence an algorithm that sorts your nodes in some particular order, right? So essentially in a directed acyclic graph, you would want a causality sequence where you say that if something happens, then the next thing can happen, then the next thing can happen, and so on, right? Nothing would go back to its parent node. So that is the point of a topological sort. So let's look at an example for this. So if a graph is a acyclic graph, in that particular scenario, we can linearize the graph so that no child node ever connects back to the parent node. So we can order the vertices of our DAG based on those directed edges. Well, let's say that we have an edge U and V, where U must always appear before, or basically in sorting sense to the left of V, where an edge would go from U to V, but not ever the other way, right? So in order to do this, we can again use DFS to approach this particular sorting problem. So what we can do is to sort, in order to sort our graph, we can call DFS on a particular graph and compute all the post-visit values for that particular graph. Now, what does that mean? A post-visit value is essentially once I am done with a particular node, I'm never going to access that node again. So the node with the largest post-visit number is essentially going to be what? Look at, okay. think about it. The node with the largest post visit number is essentially going to be a source of all other nodes. Yes, Brian, the node with the largest post visit number exactly is the last node checked. That also means that if it is the last node checked, then all the other nodes are children or grandchildren of that particular node, right? The node with the smallest post visit number would essentially be something that we are as a leaf node of a particular graph, right? So that is, we need to do this before anything else, and then we can come back, right? So we first compute all the post visit numbers for DFS. Following that, once we are done visiting all the vertices for this particular graph, we can then return a list of vertices which are ordered in terms of their post visit numbers, or in the order they are popped out from this recursion tree, right? So let's look at an example for a DFS. Okay, so we know that the time for DFS is V plus E. So the time to insert into a linked list is also big O of V. So essentially the total time again stays V plus E. So let's look at an example first. This example should also be in the book as well, but I'll go through this example. So let's say that we have this graph that connects multiple garments, is basically for a person to get dressed before they leave for work, right? So basically this graph indicates what a person needs to wear before he can wear the other thing. So a person needs to wear a shirt before he or she can wear a tie, and then they can wear a jacket and so on, right? So they would first need to wear a belt, but before that they need to wear a pant and so on, right? Blah, blah. So essentially what, given this graph, a topological sort basically sorts out this graph such that the node with the largest post visit number needs to be done at the very beginning of it, because that was found at the very end, and the node with the smallest post visit number needs to be taken care of after everything is done, right? So we can sort of perform DFS on this particular graph. Let's say we start with shirt. It has a pre-visit number of 1, goes all the way, has a post-visit number of 8. All of these are pre-visit and post-visit numbers. And essentially we perform DFS to get these numbers. Now, once we have these numbers, remember that once we are computing the post-visit, we are essentially popping out of that stack space and going to the previous node, right? The moment you go out of that node, what you would need to do is basically insert your particular node in front in order of your largest post-visit number. So first comes socks with a post-visit number of 18. So you push that in the front of your linked list. So socks comes first. Then the next one that we have is undershorts, that is with a post-visit number of 16. Right. So a post-visit number of 16 goes next, so in your linked list. Then comes pants, then comes shoes, and so on. So that is how we keep on inserting as we come out of our recursive calls. At the end of it, if your graph does not have a cycle, you would be able to find a topological sort of this nature because there is no child in this particular node here that connects back to a particular parent, right? Okay, so this is how we can use DFS to perform topological sort on a particular graph. So how do I prove that a particular topological sort works? Well, remember, if an edge is so if I find that there is no, while I'm traversing my graph, and let's come back to that particular example. Give me one second. Yes, so I started off from A, let's say, I went to B, and then I went to C. And then if I find that there is a backage into a particular DFS tree, which connects back to a parent, at that scenario, it is a cyclic graph, but that also means that C is now the parent of A. And if C is a parent of A, the post value of A would be smaller than that of C, right? So essentially, if we look at this particular graph, this would mean that there would be a backage that starts from, I don't know, tie and goes back to shirt. or some other particular node in this particular topological order, right? And that would essentially mean that there is a cycle here. When can we not get a cycle? Whenever we are trying to explore, if we come across a particular vertex that has already been explored, right? If a particular vertex is completely explored, let's give you an example of that. Let's say I have 3 nodes, 1, 2, mouse. Let's have these 3 nodes where this node is connected to this one is connected, and the white space, just let's just say 0, right? And this one is connected to this particular node, right? So sorry, other way around. This is connected to here. So this is a particular set of vertices that does not have a cycle here. Now let's say that I have this other node and this other node that we need to take care of. Now let's say that we have this particular node that connects directly to this node here, and we have this particular node that connects directly to this node here. So let's say that we started off from one of these 3 nodes, right? So if we started off from this particular node, we would first explore this, and then we would explore this, and let's say that we are done, and then we come out and explore this. So in that particular, so we cannot come out and explore this because it's a directed edge, so we are done with this thing, right? So this has been post visited. All of those vertices have been covered. So now we just move on to some other vertex, let's say this one. So once we are here, we can again start our exploration. We see that we are exploring this, and then we are exploring some node which has been visited completely. So that is not a cyclic graph. Another thing that we can talk about that is not a cyclic graph is, let's say we started off from a particular node, and when we are exploring, that has never been visited at all, even if not even post visit or never been visited at all. In that scenario, it's a non-cyclic acyclic graph. Now, the only case where you can get a cyclic graph is when you reach a particular node where that particular node has already been pre-visited but not yet post-visited. Does that make sense? When you reach a node that has been pre-visited, that basically means that you came back while searching through this entire space, and you reached a point where you already visited it but have not completed it. That is the only scenario where you would actually get a cyclic graph. Perfect. Okay. So as I said, the post values would be different, and a DAG cannot have a cycle because of DFS forest cannot have a particular back edge, as we talked about it earlier. So if an edge is a tree or a forward edge, we always know that the post value of V, where V is the child node, will always be smaller than the post value of the parent, right? If an edge is a cross edge, then we do not care about those post values because they are not going to be overlapped in any way. The pre-values, post values for one node cannot overlap the other. Okay. So now if you look at these particular nodes about in this topological order, you will notice a couple things. So note that socks and undershots and these nodes are essentially source nodes that always go somewhere to another set